Good day and welcome to ASK's online academy. Today's topic will be EXACTCAST Paddings, who will be presented by Marcus Federici. Marcus is the technical expert in feeding solutions for ASK Chemicals Europe, and I'll be moderating this talk. My name is Dave Heckman. I am the product manager for feeding systems for ASK Chemicals in North America. Some things to know about the webinar. There will be no visible names or images on the cameras allowed due to data protections. Questions can be asked via the chat function. The question and answer mode is active, and we'll try to answer all the questions on this topic at the end of the presentation. A recorded version of this presentation will be made available on our website for you to review if you had missed something. So, to begin the presentation, I will switch it over to Marcus.
So thank you, David, and hello and welcome to everybody here listening to the webinar today. I will try to lead you a little bit through the world of paddings, EXACTCAST paddings. And this is our small agenda for today. So we will clarify at first, what is this a padding? And if we know what it is, when do I need this, and how do I design it? The design would be our main focus here. And afterwards, we will go on and say, how do we create or how do we produce such kind of paddings and use it in the casting process? And after all, we will summarize a little bit and answer your questions. So at first, we will try to tell you what is a padding. So a padding is an exothermic or insulating piece of material which is freely moldable that you can put on your casting surface. It is thought that this will assist you to get a directed solidification in your process. That means it is additional tool you have beside your well-known risers and chill iron designs you use day by day in your foundries. So with this kind of padding, this is made of insulating or exothermic material. You can imagine this as a kind of additional cast material, but only in a thermal way, not in the material way. So that means you can leave your geometry of the component in a state where your designer or your customer wants to have it, and maybe just simulate the thermal issue or the thermal issues of a additional material which you normally place on that parts. So when do I need this? So the first focus we have and the main driver for using a padding is, from our point of view, always the feasibility of a casting component. That means in every case, if you have any issues by a feasibility of or a castability of a casting, you can use a padding when there are problems in feeding distances, difficult to access residual solidification areas, and if you have any issues by or if there is a change in geometry need that you can then you can realize a feeding there, you can always think about use a padding in this way. So a padding is therefore very good for lightweight constructions where you have a lot of bosses which thin walls connected. Here you can have huge benefits, and also if you have no place for your risers in the mold box, or you have huge ways to go with your feeding distance, then always a padding may be a good solution here. And also you can save costs for removing your additional casting material as we show you in this small example. So this is a very simple steel casting geometry. It's a ring-shaped geometry where you have, as you might know it, some bumps on the sides under the riser so that you can have the right feeding distance, that your feeders are working and your feeding solution is working. And what you can do here with the padding is you can just simulate in a thermal way these kind of bumps or this kind of extra material with this exothermic padding you put aside direct under the riser. In that case, we can save about 30 hours of fettling time, and we have, of course, a less casting weight of the total component here. So therefore, you can. This is a very simple example which we can show you here, but this is a good working solution and shows you about the opportunities you will have by using paddings in your casting process. So what are the advantages using these kind of materials? So you can improve yield. So this you can manage by different steps. So you can combine riser. You can try to feed more than one node with one riser by combining them and make the feeding possible over there. You can save cleaning costs, as you can see in the small examples. You have shorter time to market with your casting because you have no changes or not that much changes you have to discuss with the designer of the component, so you can react much faster. And in that case, you can also expand your foundry's portfolio of castings because you can do parts which you maybe were not been able in the past to cast them before. So you have a high degree of freedom in the geometric way how to design it, because it's more or less the same degree of freedom you have with a code box core or a core itself. It's easy to operate, and you can use it in core sections as well as on the molding side. Therefore, you can reduce the total weight of your components dramatically, and so you can also help your customer and the designer because they're always looking for savings of weight in their components and in their castings. In the next few slides, we would like to show you how you design such kind of paddings. So we will check how this is working. So we start with a geometry which is imaginary, but I'm pretty sure you have seen those kind of geometries in your daily business in a foundry. So this could be a single connection plate, or this could be also a part of a bigger housing, like a crankcase or something like that. In many cases, these kind of geometries are used to bring two components together to screw another component on a housing or something like that. What we normally do here is that we try to feed this with a standard riser, either exothermic or insulating or whatsoever. You can place this above the geometry and try to do that. But as you can see already, when I place a riser which is the right size, or the modulus you have to use here, you see there is no space for placing on every boss a riser. So we have a issue here with our standard riser placement portfolio. So I think this is not a well-known thing in a foundry. So also the simulation result here is quite unsatisfactory. That you can see on the left hand, you have the hotspot of the casting, which means the residual melt areas, or the areas where the last solidification takes place. And depending on that, we also have the porosity on the right side, and you can see that in all the bosses you have porosity in these castings. And the problem in many cases is these bosses you have in threads or holes or something like that. So during machining, you will open these porosities, and mostly this will be seen as scrap, and this is every time an issue. So we don't want to have that. So what is the first thing we can do? As I first mentioned, maybe you can imagine that it is, or the padding material makes the component behaving like I add material. And the easiest way for me would be if the plate was massive. So that means we just take it and fill it with exothermic material. In that case, you just bring in the exothermic material, and you place a riser sleeve on top. And to have a better separability, you can also add a breaker edge here, and the rest of the geometry of your padding is the negative of your casted component. So this one we will put in simulation and check for the results. The next examples, when we show some videos, it's always the solidification of the casting show. That means we show the fraction liquid, and everything which is already solidified, the material will be faded out. So we will start with our first video here to check for our solidification. What we can see, there is a huge difference between the solidification behavior in these two components. On the left side, you see the design with the padding. On the right side, you see the design without the padding, with a standard riser on top. So what you can see is that your walls are freezing very early, in a very early stage during solidification, compared to that geometry with the padding, where the walls stay a long time longer open and enable solidification through those thin walls towards the riser. So you have a perfect directional solidification. Even if you just have thin walls, you just keep them open with the energy you put in with the exothermic material, which we call the padding. So that means for us, if we compare the hotspot and the porosity of the same casting, just with two different ways of just with and without padding, you can see the hotspot with the padding is just in the residual riser. Without the padding, you have the hotspots as seen in the first slide within the casting. And of course, the porosity behaves in the same way. That means that you have a sound casting here with a padding, and without the padding, you have the porosity and the issues in machining. So that means that was a very good first example. It was a hit in the first shot, which is always nice, but we want to show you also that there can be some restraints you have to consider. So therefore, we will also have a look on the second geometry, and we want to show you that this design of a padding is mostly an iterative process. So you will test a way, you need to simulate, and then you check for the results, and so you can find the best way. But it's as you will see, there's always a movement in that position. So in that case, we start with a fitting, a hub, a flange, whatever. So it's a geometry which is also not very rare in the foundry business, and especially here we have a a narrowing section which will part the solidification in an upper part and in a lower part. And this narrowed section will freeze in a very early stage during the solidification process. So we will have big issues by feed this part through the wall without a padding. So the standard a standard way of doing that is to place 2 to 4 risers. We decided here for 2. We will have, in that way, we will have this upwards casting position to save space into the molding box, because if we turn it 90 degrees around, we will need a lot of more space, and we also have a limited riser range of the side risers we would use then in that case, and therefore we go here just with 2 risers on top, because this is for the process the most easy way to access this. But we already see, or we can imagine, that we will get in trouble with our narrowing section. So in our first example, we just added material there where you as a foundryman thinks, okay, if I would cast this as a complete casting, I will add material in that narrowed section, which is the first approach we can do here. So what we have to do is we add here the padding material, or the exothermic material, and we need a little core print to embed this into the core. This can be by gluing, or you can also shoot this, or whatever your process is able to do. You can coat this or let it coating free. Both is possible as you have it in your process the best. So let's check for the results in our simulation. And we compare again on the left side with padding, on the right side without. And what you can see very, very clear is, as we estimated, on the right-hand side, you can see that the solidification is dividing in 2 areas, which are solidifying parted in an upper part and in the lower part. And on the left-hand side, you can see the solidification with the padding, and you can see it behaves indeed like if it is one piece here. Because of the core print, it's a little bit also directed in this section. But if you just look at the isotherm behavior, you can see this behaves more or less like a full casting here. But I stop it here. You can see our problem. It's behaving just in the thermal way, like extra material in that way. So we have no material transport through the padding, which is, of course, you can imagine that this is not possible because it's not steel or iron or type of metal. So therefore, you will also have here a section which is not connected to the rest of the solidification, even if it's in a thermal way, looking good. So let's check about our porosity for this solution. And what we can see is, okay, with the padding, we can move a little bit the porosity upwards towards this narrowing section compared to the version without the padding, but we are not really satisfied with the result. So we need to check if there is another solution. So the base meaning of the padding is working, so that it's behaving or that it's putting energy inside, and that it's taking this to a solidification which is more or less like you have extra material, but there is no material transport through the padding. So what to do next? So what we have to do now is we need to get solidification on the outside around this narrowing section. That means we need to place the padding not inside but outside. And so that we get also in the molding line a good behavior, we need to fill this this area until the flange, because otherwise we will get an undercut. And so we have to fill it completely up to the flange starts. So this will be our next approach with a padding. And we will check here for our simulation result. Again, we look at fraction liquid, and we can see the behavior here of the version without the padding is still the same. And we can see, okay, this is working quite well, because here we are more or less, we can move around the narrowing section. But if I go step by step in the solidification, we have another small issue, because now we have, due to the huge energy I put in through the padding, my solidification time of the component raises a lot. And therefore, as you might know, the solidification time is also determining the module of a casting. That means now we have an issue that I have a riser on top, and I have a small section here, which could not be feeded anymore, because we need a little bit more feeding power. So we check for the porosity, and we see exactly that. So it's much better. The picture now is much better, but we still have 2 spots of porosity directly under the riser. That means here we need also, if you design a padding, you have to keep always in mind that you are influencing your solidification time with that. That means if you put more energy inside and more heat inside, the solidification time will get bigger, and so your modulus will also grow. So you need to answer that with, or you need to consider that in your feeding concept. So what to do now? So we have 2 possibilities. That means we have 2 ways for solving this problem. On the one hand, we can adapt our padding. We can reduce the thermal potential of the padding. That means we can either try to make it smaller, but in that case, what we check here, we have that issue with the undercut if we make it smaller on top. And we also have the possibility to get less energy inside by less energy containing mix of the padding. But we need also to make sure that our narrowed section will remain open until this point of solidification when it's going up. So therefore, this may have some difficulties and is also very hard to detect. So therefore, there's also another option, that we increase the thermal potential of our risers. So in the first way, we can just take a bigger riser. That would be an option. Or we can also use a hotter mixture, or a higher, or we can put more energy into the mixture of the riser. And in many cases, this is the most cost-effective solution. So you need not more space on the plate, so you have more or less the same riser. But if you can put a little bit more energy inside, and we see this was not so much we need here, so maybe this could be a solution for us. So we take this, and here we have, and we look at the simulation just with our riser mix with a more power in our mixture. So what we can see is our behavior, what we have seen before already. So we also have a very clean solidification around our narrowed section. And I take it picture by picture. You can see now we have a perfect directed solidification here. And that should see also in our porosity analysis. So that means, as you can see here now, you have a sound casting compared with the version without the padding. What you also can see is that the total void volume in your risers on top is much bigger than in the version before. That means also your risers become more effective here, because all the volume deficit the steel has here, or the iron has here, is now on top in the residual of the riser, and not in the casting. So now this is a solution maybe we want to try. I just want to show you how this is, why this is working in that way, or what you should consider here. So this is one more time this module comparison, and you can see that the module of your casted component from the beginning without padding is raising as you put more and more energy with the padding inside. That means also your thermal modulus of the casting, unless you don't change the geometry itself, but just by putting more energy inside, is a little bit or becomes higher and higher, and therefore you need to consider this also in your feeding solution, or in your in your feeding process. But what you can see also is that from step to step to step, you become also, from with each iteration, you come closer to the target. And this is what you can see. So normally, so this is the way we want to show you how to develop from the beginning on, step by step, kind of padding, and so that you know the padding is just one part of your feeding system. So you can also, it's just another tool to get a directed solidification ready for your casting. So all your other tools like chill irons or like feeders are still needed, but here you have more possibilities, and you can widen your portfolio, and you can achieve feasibilities of castings which you normally could not. Okay, so we have a software solution. Now we need to get it as hardware. So how can I now get this into my real casting, away from simulation into the foundry? So at first, there are two ways of handling a padding. So the first one is that you order direct at ASK a ready geometry, so a ready to use piece, which you can, or ready to use padding, which you can just put in your molding box or in your core box, and that's it. But there's also another way. You can do this also on your own. So you can also get from our side these exothermic or insulating mixes and produce a padding or what you need in your foundry process for yourself. But therefore, we need to take into account some thoughts. The first one is, what kind of mix do I need? Do I need an exothermic base compound, or do I need an insulating base compound? The exothermic base compound, of course, have the maximum effectivity. That means you have here almost a 1-by-1 replacement compared to casting material. Of course, just in the thermal way, as we've seen in the example. Your microstructure corresponds to the solidification time. That means if you put on exothermic material and you have a higher solidification time than normally a wall thickness should have, you need to consider that. But this is not only a threat, this is also a chance. So in cases that you have to suffer from hard edges or from white iron inclusions or something like that, this could be also a way of solving that. Then you have also inside the exothermic mix, you have some elements which are reactive, because you need this for exothermic reaction, and all these components should be considered that they can also react with your melt, but you can avoid that or limit that by using a coating here. So if you need some expertise which kind of coating you use best and which is the best one for your kind of process, please refer to our coating experts. They will be glad to give you here some good choices. Also, you are limited in the choice of binders because the exothermic material has some components which may react with some other components in some binders, but we will come later on this issue. And of course, if you want to do that in your core shooter, or you want to produce a padding in your core shooter, exothermic one, you have to consider also some explosion protection measures and also for some other safety issues. But we can help you here if you have any questions, what you need to realize that. On the other hand, you have an insulation-based compound. So there you have an almost unlimited choice from the binder point of view. You can more or less easily shoot this on your own core shooter. The materials used in the insulating base compound are more or less have a neutral behavior or an inert behavior. That means no reactive materials are inside. So this is a big point. But you have no additional energy input through this insulating padding that you need to consider. That means you can keep your heat, which you bring in by your melt, longer in the system, but there is nothing to bring on top. So that means it's in most cases much more material is necessary, and in some cases also the effects of an exothermic padding could not be reached with an insulating one. Also, some alloys are only possible with an insulating base compound. Staying with the exothermic compounds. So in our portfolio, we have some different exothermic compounds which we can use for the paddings. You have the choice of how much energy is in the mix and also how fast the ignition time or how fast the ignition will take place, and also the fire resistance you can choose here for this different type of mixes. So you have some things you can combine here. This is depending on your casting alloy, your size of the casting, and some other things. But please feel free to contact us, which could be the best one for your casting. We will help you here. We strongly recommend, of course, in ductile iron to use a fluorine-free formulation to avoid any graphite degeneration on the casting surface where it gets in contact with a melt. This is strongly recommended here to not get in trouble with your graphite formation. The mix is in principle designed for a cold box use. That means cold box and PEPSET are the main binders you should use here. So there is maybe a solution for another binder like Linocore, maybe also a silicate one, but you will not receive the surface quality and the properties you will have with the cold box process or the adequate no-bake process with PEPSET. Please don't use it together with any acid hardening binders or alkaline phenolic resins or silicate esters, because here we can have already some reactions between the binder and the exothermic mix. So this is not recommended. If you have any questions about that, about quantities of use and how to do that and what you can use here and what is possible, So please feel free to ask our team, and you will find a very good solution for that here. On the other hand, you have the insulating compounds. Here you have our EXACTTherm SDL210, which is a very lightweight insulating material, and you can mix this with sand. The graph you can see here is a curve about the mixing or the blending value of this one compared to the thermal conductivity. And you can see the more you put in of these lightweight material, the lower the thermal conductivity gets and the better your insulation properties are. But also here there are a few limits, especially when you shoot this on a core shooter. You need a little bit of sand to keep flowability in the system. That means you need a little bit of sand so that this very light mix is going into your core box and fills it in the way you want to. And then the last one, please also, as I said, this is a very lightweight material. That means we have a very low bulk density of the material. And of course, with that, the amount of binder is raising here. In principle, all organic binders are suitable for that process. You can also use inorganic binder systems, but they will higher the thermal conductivity, and also the surfaces could be not that nice as with an organic binder, especially in long solidification times and high temperature alloys. So using this in some smaller castings or with low solidification times, it might be possible to use also an inorganic binding system, but recommended here is an organic system. So, and this was from my side already all for today. So please, if you do have some questions, please ask them.
Well, thank you, Marcus, for the very informative talk. I think we have some questions already put in the chat section. The first question is, can I use paddings for aluminum castings as well as ferrous castings?
Yeah, yes, of course, you can use a padding for aluminum casting. The only thing you should keep in mind is that the exothermic one is designed for iron and steel, or let's say also for copper-based alloys. So what we need to consider here is the burning temperature of these exothermic paddings, and therefore we strongly recommend to use the insulating ones for the lightweight alloys or the alloys with a low melting temperature here.
Okay. Second question, are there any impacts on the casting surface and or microstructure of the padding contact area? And are there any specific alloys that may have more reactivity with the padding technology?
Regarding the first thing, of course, you have an impact on your microstructure as described. So you have a higher solidification time that you need to respect, but you can also work against this with any type of inoculation or some other things you use for thick wall castings, because you need to treat it as a thicker wall than it originally is. The surface quality of the padding is quite good because of the high fire resistance of the base material we use here, and together with the cold box binder, we have very smooth shapes. So there is no burn on or something like this we have seen in the past. So you get very good surface qualities also with the padding. And of course, with the alloys, you need to make sure that either you coat the padding, or your alloy is not reacting or does not get harm of specific elements which are in these paddings. That means if your steel is a little bit has an issue when it contains some aluminum or magnesia or whatsoever, then you need to coat the surface so that these elements cannot go into your casting or into your melt during the process.
Great. The third question, is there any rules for padding design from a dimensional point of view?
Yes and no. In general, not. So you have the same restrictions as you have it with a core, for example. So the big you can build your core box and your core shooter is, you can do a padding. If you want to have a ready-to-use solution from our side, we are restricted to a specific size. So we just have the possibility, which is the biggest size our core shooter can do. But I'm pretty sure we will also, if it's bigger, we will also find a solution to get things started. But there are, of course, some restriction in the size. From the process point of view, no, there are no restrictions at all. From the size. So we have also very huge of these, mainly hand molded with PEPSET.
Okay. And regarding the mention of PEPSET, are there any recommended ASK binders for these paddings?
Sure, some binders get work, or especially when you use it in the core shooter. There are some binders which work a little bit better, but I think this is also depending on the cast or on the padding's geometry and the type of the core shooter you use and the process parameters. So to say in general, use this or use that. So definitely there is a starting point or a binder which is in a general use binder, which is to start with. But it could be that you also find another one which is in your process better or not. But I think we can discuss such kind of things more deeply in a personal meeting when there are some more facts on the table. But in principle, all of them are able to shoot a padding.
Okay. Is there any limitations to the casting weight or material grades?
Not really. So this is more or less the same thing with the size of the padding itself or of the core box. Of course, you can have for very small castings, you can use that, and you can use it also as well for big ones. So you can scale this. The point is, you need to handle this, or you need to handle this. So you need a mixer which is big enough to have the right amount of that, and you need to move it in your foundry. But if so, I would say no, there is no real borderline. But just try it in simulation. If it's working, I think there should be no big showstopper from our point of view.
Okay. Next question is, how are the gases generated from this exothermic pad, and how are they vented out?
So this is a good point. So you need to consider that you need, especially so you have a higher binder content, because your binder or your mix is not that homogeneous like you might know it from a coat box or from a standard core made of silica sand. So you have a lot of different grain sizes, from very, very small to quite big. and so you need a lot more binder in the system. That means you have a lot more gas here. So that means you need to make sure that the venting is crucial, and also you need to make sure that the venting is working in your process. It means in case you set this on the outside shape, it's more or less easy to drill this open and to vent this towards the mold box wall. In the inner core section areas, you need to make sure that the core venting is working quite good. But there is, of course, a risk for a higher, or there is a higher gas potential by burning these paddings, especially also in the exothermic ones, because they are burning completely. That means normally in the cold box core, if you have a very thick core, the inside will not burn the binder. In an exothermic padding, the complete geometry will release the gas potential of the binder.
Okay. The next question is, are these materials in magma?
Yes, of course. All the materials I showed you before are already in as datasets in magma. You may find them in the new database we have in the latest version of MagmaSoft, and you just need to set up them right. So you not only need the material right, also the heat transfer coefficient, which is given. If you have any questions concerning that, also our colleagues from Design Service or we can help you with that if you don't find the right ones. But in Magma, all data are implemented.
Okay. The next question, is there any limitation of the thickness of the casting that where it needs a padding?
It depends a little bit on the size of the casting. So, of course, if you have a real huge casting with a wall thickness of, I don't know, 1 or 2 millimeters, let's say, or in that way, you need to consider that you need a little bit of time to start the exothermic reaction, so it's always when you put in your padding, it will have ambient temperature, and of course, in the first way, before it starts burning, it will take away some heat, and then it will start burning. And so there, of course, there will be a limitation on thin walls that will work or not. So, but that we need to find out. So in that case, yes, there is a limitation in wall thickness on the lower side. On the upper side, yeah, it's hard to imagine, but it's more or less than the same story. Like in size of padding, size of casting, it depends a little bit on what you can handle and what is able to degas and all these things. But of course, the more critical one is the wall thickness in the lower area, or in the smaller area.
Okay, and I think we have time for one more question. Has there been any differences in the solidification mechanicals where you're using a padding with different alloy steel or maybe special grades? And does this work more predictably with a certain alloy or metal grade than maybe another type of metal?
Okay. Of course, you have different solidification behavior and different types of metal. So the point is the padding adds more heat, and of course you need to check then very clearly already in simulation or whatever you use for that about the real solidification times, especially in the areas you want to check out. So I think there are pretty much criteria you can use in your simulation software to detect that. So what you can see is that the padding is just a source of energy in your system, more or less. So that means in some ways this can help, but also this can be not so good. So if you have a different solution, or you have an alloy which is or you have a steel grade which is turning quite early into a thick state or into a solidification, which is not so easy to feed. There can be issues, but your normal criteria, you normally your simulation in the same way, because we just put in an additional energy source here.
Okay. Well, thanks very much, Marcus. I think that was a very informative presentation, and all the questions that you have answered are, I think, very helpful. We were not able to get to all of the questions. We have a note for the questions that are there that we haven't answered, and we'll have a local ASK representative reach out to the people that had those questions to try to get you some answers, or you can reach out to them to try to help facilitate that. This will conclude this presentation. Please stay tuned to our website for future presentations that we'll be doing. These will be coming out every so often. And by looking at the website, you'll see when these free online webinars are available. Thank you, everybody, and have a great day.